Okay, in this last tutorial, we're going to look at standing waves once again, this time open at both ends. Now, in the previous examples, we saw that if a standing wave is produced and there's an open end, there's always an antinode. Well, in the case that there is an open end at both sides, you still get antinodes on both ends. Now, this is very unique. If you imagine holding on to a ruler in the middle and then shaking it up and down, you'll notice that at the fixed point where your hand is, there's a node. And that at the other two ends, you're going to get an oscillation happening. And that oscillation is at the first harmonic, so F1. And it's the first harmonic, the first resonance length. And we know that there's an antinode here, but you can't have an antinode in the middle. It'd be impossible. So what we know is that there must be a node in the center right here. Okay. So with that, we know that we would draw the harmonic like this. And you can imagine it sort of vibrating about the center point and getting these two antinodes at either end, right here and here, and a node at this point. Now, the equation, as you see at the top, is identical to fixed at both ends. So the first resonance length happens at 1 times lambda over 2, which is lambda over 2, which is 0.5 lambda. Let's see if that makes sense. L1, so it starts in an antinode and goes to the bottom of an antinode. Well, from antinode to antinode, that's always a half of a wavelength. And there we go. Okay, you can grab a ruler or some sort of thing like that and just kind of shake it in the middle, and you'll see that it'll go on both ends. If you double the frequency and hit the second harmonic, then the resonance length is 2 times lambda over 2, which is just lambda. So there should be one wavelength. So you're going to get or another way to think about it, there's a quarter here and a quarter there. A quarter and a quarter is a half. So you're going to get a quarter and quarter. So it's going to look like this. So if you were able to vibrate it or hold it in 2 points and vibrate it like that, you should see that you would get an antinode in the middle. It's open at both ends, so you get 2 antinodes, and then nodes at the 2 fixed points that you're vibrating the material at. Now, if this is an air column, like a tube, and it's resonating, like in musical instruments, bottles, all kinds of stuff like that, then if you blow over the top, you get a standing wave set up. That's the sound that you hear, that standing wave, that really loud harmonic. And at the first harmonic, it would be a half a wavelength in there. At the second harmonic, the wavelengths get shorter because the frequency got bigger. And you would see that there's 2 nodes inside there. If it's air that's vibrating, that these are like compression waves, and these are areas of maximum compression and really high pressure and really low pressure. If you've ever opened up 2 windows in your car, you get standing waves. So if you're driving and you have 2 windows open, just a little bit, and maybe not another one, you'll actually set up a standing wave in between your car, and you'll have areas where there's really high pressure, these antinodes, and really low pressure where there's these nodes, and it's very uncomfortable. You'll hear the boom, 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 and your ears will start to hurt, and that's because you're in these areas of high pressure or low pressure. And if you move your head around, you can actually find the points where the nodes are and where the antinodes are, depending on the speed that you're moving and all that kind of stuff. So give it a try. So it's pretty cool. Now, here, let's take a look and see if it is, in fact, one wavelength. Well, there's a quarter and a quarter, which is a half. There's another half. Oh, look at that. One wavelength. Because node to node or antinode to antinode is one wavelength. And then from a node to an antinode is a quarter. So a quarter, a half, and a quarter makes one. Third resonance length, just like before, 3 lambda over 2. We're now at 3 times the fundamental frequency. And there's going to be a quarter and one in the middle. And so here we go, like that. Like that. Quarter, quarter, one full one. Well, that is clearly 3 halves of a wavelength. There's 1.5 wavelengths inside there, right? Look, a quarter is a half, 1.5. Easy. Again, antinode, 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 node, node, node. Next part, fourth resonance length. Okay, and again, we're gonna have the quarter, and then there's gonna be 2 inside there. Notice how I'm making those a quarter of the half as best I can. Like some of you are gonna, some people are really good at drawing these, and like other people it gets a little challenging. So you have to keep that in mind. Antinode, 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 node, 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 node. And here we have a quarter, which is 1. There's 1.5. Sorry, a quarter is a half. There's another half. So that's 1, 1.5, 2. So L4 equals 2 wavelengths. And notice it just like before, it always goes up by half a wavelength. Half, 1, 1.5, 2, 2.5, 3. You can get the point. L4 is 2 wavelengths. Or you can just look, there's 1.5, and then a quarter makes 2. So easy. Okay. Example. An open air column is vibrating at the 3rd resonance length. So that's way down here. So this is the situation we're looking at, the 3rd resonance length. Again, you can even recognize the 3rd resonance length because if you want to think about it, it starts in antinode. There's the 1st, 2nd, 3rd resonance length, right? Because they have to be at antinodes. So that's another way to count them. You don't count the first one. You just go 1, 2, 3. Oh, 3rd resonance length. Look at this one. Don't count the first one. 1, 2, 2nd resonance length. Don't count the first one. 1st resonance length. Don't count the first one. 1st, 2nd, 3rd, 4th resonance length. Okay? So that's how you can always do it. You just don't count the first one, and then you count the lengths from there. And they have to end because it's open at that end. Has to end at a antinode. All right, so the air column for the 3rd resonance length is 25 centimeters, which is 0.25 meters. The air temperature is 28 degrees Celsius, which means that the speed of the wave is 332 plus 0.6 T. And so if the temperature is 28, you go 0.6 times 28 plus 332 is 348.8. Okay, that's the speed of the wave since it's sound in this case. And it says calculate the frequency. Well, speed equals frequency times wavelength. So frequency is the speed over the wavelength. Now, we know the speed, but we don't know the wavelength. So we use our information about the resonance. Well, L3 is 3 lambda over 2 for open at both ends. I mean, you can see the diagram right here. So if you're trying to solve for lambda, it's 2L3 divided by 3. So it's 2 times 0.25 over 3. And so the wavelength becomes 0.5, let's say 2 times 0.25 is a half divided by 3, 0.166 meters of the wavelength, right? And it makes sense that if this is 25 centimeters, from there to there is about 16 or 17 centimeters. So now the last part is, since we've got the speed and we've got the wavelength, we just solve for the frequency using the equation that we had there. So the equation was 348.8 divided by 0.16666. So 348.8 divided by 0.16666. It's a frequency of about 2093 hertz. So it's a pretty high frequency. Okay. And that's how you solve problems like this. Pretty much every problem from here, like resonance or standing waves, whatever, if you call it resonance or standing waves, it doesn't really matter. It's all the same thing. It's all using these formulas or these diagrams to solve the problems. Okay, now you can work on the problem sets.